Что-то я не нашел объявления. Может, я его забыл послать? Ты говоришь, ничего не слышно, что ты говоришь.
Сейчас, не исключено действительно, но подожди, но вроде как мне какое-то объявление пришло там про теорему Кравцова там и ее изложение, то есть, ну, может быть, это все так уже надоело товарищам за предыдущие разы, что они не склонны слушать еще раз, но, по крайней мере, сами товарищи котоводы вроде собирались прийти. Потому что они как раз интересовались, как это можно объяснить доступно.
Нет, послал я смотрю, я послал.
Ну, не знаю.
15 ноября.
Тут я в 6:30 должен что-то рассказывать, но вот, оказывается, есть Zoom поблизости. Какое-то время, по крайней мере, я надеюсь. Тут в городе Пафос на Кипре имеется университет имени JetBrains и Саши Полякова. В нем даже есть бассейн.
Что-то у тебя там столько помех в этом самом. Шумит чего-то.
Ну ладно, я так.
Значит, я сразу хочу сказать, в рассылке семинара указана не та ссылка на Zoom, не эта, которая здесь. Поэтому
Вот в чем дело.
надо, чтобы... И там указано на семинар лаборатории теоретической информатики. И там никто ничего не начинает.
Понятно, сейчас мы это самое...
Надо написать сейчас, я, может, смогу я записать. Так.
Сейчас, а мы не можем начать там, интересно?
Ну, там наверняка у вас кто-то из высшей школы экономики должен начать. Нормально.
Сейчас посмотрим.
Не, ну раз мы тут, можно просто... Сейчас я напишу. Сейчас. Ну, давай уже. Сейчас reply all. Be correct. Zoom link. Так. Сейчас. Не, ну. Да.
Я проверил, действительно, там неправильная ссылка. Извиняюсь очень.
Я, кажется, послал правильно.
А кому вы послали?
Ну,
По
всем.
по рассылке, да?
По рассылке, да. Мне кажется, сейчас я жду.
Сейчас я посмотрю, что вы послали. Что-то я что-то не вижу, чтобы я что-то получил совершенно в этой рассылке.
Мгм. Ну, сейчас еще раз попробуем. Ну, или вы пошлите. Сейчас.
Давайте, сейчас я пошлю.
Ну, давай я. Давай. Нет, что-то у меня не работает.
Так,
Пошли.
сейчас я правильную ссылку сначала
Почему-то
скажу.
она иногда в спам попадает. Может быть, как-то так отправляется.
Command-C. Ну что, получил кто-нибудь по рассылке? Саша, вы
Да.
получили?
Да, я получил. Да.
Сейчас, Даня, что-то так плохо слышно, что вы говорите.
Я тоже получил.
Вот сейчас
вот,
лучше.
да, и видно, что люди присоединяются.
Здравствуйте.
Добрый вечер. Извините, что я так это невнимательно ссылку поставил.
А к той ссылке доступа нет, может, туда может присоединиться и
А
сказать.
нету, но это надо просить эту самую менеджеров в вышке открыть.
Понятно, да.
Вот, но и к тому же это время может быть забито уже кем-то другим.
Не, в смысле, что я туда
Здравствуйте.
присоединялся, там как бы ничего не было.
Ну, дело в том, что там может менеджер только эту самую
понятно,
конференцию запустить.
Мгм.
Да. Простые работники на это недостаточно квалифицированы.
Ну, не в том дело, а в том, что ресурс это ценный, так сказать. Thomas is here. Thomas is here. So
Yes,
I
hello.
switch to English. Hello.
Thanks.
Okay, I think that it's time to start now. Mm. So I will start with very simple things. What is that the set A? By the way, I will share the blackboard. First of all, I will share the link. Let's see. What is the link? So this is the link to Jamboard, and I will also share it on the screen. So we will consider, say, subsets of natural numbers, and such a thing is called computably enumerable. If there is a machine without, or machine or an algorithm without any input, which prints the list of all elements in some order, separated by comma, say. If there is a machine D that prints the list of A. So here is D. D has no inputs and it outputs all the elements. Now, similar to how Kolmogorov complexity of finite sets or finite objects is defined, we want to define the Kolmogorov complexity of an enumerable set A. Informally, the complexity we will denote it by CA. C means complexity and E means enumeration of A as the minimal length of D, of such D. To define this formally, we need to fix some universal machine, some universal algorithm. Call it, say, call it also D. D then receives some finite strings P as input and enumerates some set as output. By the way, this output set can be either infinite or finite. Even in the case when it is finite, the machine provides no indication that the list of elements is complete. That means that we do not know whether it will print something else or not. So this is very important in what follows. And if such a D is fixed, D with an auxiliary, with an input, we define enumerative complexity of a set A with respect to this D as minimal length of P such that D with on input P enumerates this set A. We just write it that D of P equals to 8. This is very similar to defining Kolmogorov complexity with respect to a fixed description mode. Here, D is understood as a description mode, but instead of describing finite objects, it describes infinite objects. It describes enumerable sets. And this definition, of course, depends on the choice of D. And to make it independent, invariant, we need to fix an optimal D. And a theorem states that such D exists. So there is a D like this, such that for all D prime, for all our algorithm D prime, we have that the complexity with respect to D is at most the complexity with respect to D prime plus some constant, which depends on that D prime. And the proof of this theorem is quite standard. So this D interprets the first part of its input as a program of another D prime written in a prefix-free mode, call it P, and then followed by some other string Q, the rest, and then it just uses the algorithm this program P, an enumerating a description mode with program P applied to Q. So this is sort of P applied to Q. And just by construction, this this description mode is optimal. If A is enumerable, then it has some finite complexity, which is easy to see. If A is not enumerable, we will assume that its complexity is infinite. Now, we want to define a similar thing called a priori probability distribution, or just a priori probability on subsets of n, of naturals. This is defined using another type of machine. Now we consider a machine, say U, which is probabilistic. So U is a probabilistic algorithm or machine. And again, without input, like in the case of defining enumerable sets. And also we assume that this machine has an output device where it can print infinite or finite list of natural numbers again, separated by commas. And to any such machine, we assign the probability that U prints a specific set A. And this will be denoted, say, by P with subscript U of A. And now we want to define the following thing. For every U, to every U, we assign such a probability distributions on subset of n. And we want to consider, make this independent on U. To this way, we again compare different U's, and we say that some machine is better than another one, then if the corresponding probability distribution for the first machine is larger than the distribution for the second machine, times some positive constant. And again, one can prove the following theorem, that there is a machine U like this, a probabilistic machine U, such that for all other machine V's, V, the corresponding probability distribution for U is at least the probability distribution for V over some positive constant C. And this constant depends on V. It is constant in the sense that it doesn't depend on A. So this holds for every A. And again, we fix such U. And we call this guy a priori probability distributions of enumerating a set, denoted by A from a priori, E from enumeration of A. So by definition, this is the probability that this is enumerated on a universal machine, on this one. So we fix some U from this definition, so fix U, And also we fix D from the previous slide, which defines Kolmogorov complexity of enumeration, D. So we obtain two quantities, AEU and AE, a priori complexity of a priori probability of enumerating a set, and also we obtain C. Is it clear so far? For example, is it clear why the second theorem holds? Sasha Kazachinsky.
Yeah, well, I guess we can devise a machine that first, I don't know, let's say takes, so it has a, sequence of random bits. It has a tape of random bits, and it reads how many zeros there are in the beginning, and then runs the corresponding machine V. You know,
How many
there are
zeros
k.
and then one, right?
Yeah, like the
So-
largest prefix of zeros. If it has k zeros and then one, then it reads runs the k Turing machine on the remaining random bits.
U on A to the SA K 1 and some omega just runs kth machine, kth Turing machine, assuming that its random bits are omega on omega. Right. And to this end, in this way, we obtain U, which is approximately to the minus K thus as the kth Turing machine. So this constant will, which is denoted by C, V will be approximately 2 to the minus the number of that machine. Okay, this so we have two definitions, and we want to compare these two notions. In the case of finite objects, we know that more or less one of them is exponent of another one. So for finite objects, the complexity, the a priori complexity of a finite string x is approximately equal to the 2 to the minus the Kolmogorov complexity of that string. But that's for finite objects. And my talk will be devoted to a similar question for infinite objects, for subsets of naturals. First of all, we need to understand a simple thing. Is one of them first of all, we need to understand inequality in one direction. This inequality is the following one. If C E of A is finite, that means that A is enumerable, it has a program. Then A E, the a priori complexity, is positive. So why is this? So for all enumerable sets, their a priori enumeration, a priori probability is positive.
Well, I
And
don't
no-
understand. Don't we just have a machine that deterministically outputs this A? And this means that a priori is at least one times some divided by some large constant, but then it's positive.
Right. And then we also have the implication in the other direction. If a priori probability is positive, then A is enumerable. That means that its enumeration complexity is less than infinity. And do you understand also, Sasha, why is this?
Well,
This is
because if
called
it's
this is
positive,
called the theorem of somebody, the Leo Moore Shannon Shapiro.
Well, then I'm confused why I should understand this if it's a theory of somebody. I thought that it's just
No,
because
it's a
we
very
can fix
simple
random bits.
theorem.
I mean, there exists a fix. Wait, sorry, no, sorry. I don't understand now.
Maybe Bruno is here.
Oh, I wanted to say that I mean there exists a fixation of random bits that prints this set, but then this is a computable fixation of random bits. I mean, so how
but
should
why
I?
is the computable fixation? This is not clear.
Yeah. So it's not obvious. So
maybe Danya knows.
um,
Yes, I'm sorry, I was a bit away.
So we are
So
discussing the following two implications. I mean, A is enumerable if and only if its a priori probability is positive. So in one direction, this is easy, as Sasha said. If A is enumerable, then we can consider deterministic machine that prints that set.
Yes.
That deterministic machine can be considered a randomized machine. So with respect to that machine, its probability is 1, and hence with respect to the universal one, it is just positive. But in the other direction, it's not so trivial. Assume that some randomized machine prints a set with positive probability. Why it's necessarily computable, enumerable, computably enumerable? So the proof is like that of this theory. So assume that a complexity of outputting that set, that the probability that our machine U prints A is positive. Then using a standard theorem from, actually that means that this implies that for some other machine, call it V, for example, the probability is as close to 1 as we want. We can construct a V for which the probability is, say, larger than 1/2. So this is a consequence of the following theorem from the measure theory. If a certain set has positive measure, Lebesgue measure, then in some interval, it has a measure larger than, say 99%. Or at least we need to fix an interval that is a finite string x, such that the probability that V prints U prints X, assuming prints A, assuming that the randomness used by P starts with Z X is larger than, say, than 1/2. Danya, do you believe in this? Sasha.
Mm. Why can't have 1/2 in every interval for some set? I don't understand.
No, imagine, say, a measurable set on the plane. Then
Yes.
what means that it's measurable and it has positive measure? The measure is defined as follows. We consider simple set, and simple sets are union of rectangles or whatever. In our case, in the case of the plane, in the case of the omega, it is the union of intervals. And we consider sets which are close to our, such unions, finite unions, which are close to our set in the sense that the symmetric difference between this and this is very small, larger than certain epsilon. And when epsilon tends to 0, the sum of measures of these simple sets is equal to our set. So assume that A has a positive measure. Then we can take as epsilon that measure of A over, say, 100. And we obtain a simple set whose symmetric difference with A is less than the measure of A over 100. That means that if we intersect A with all these sets, in some set, it should have a very large measure, at least 1/2. So anyway, this is a standard theorem from the measure theory. And if we have such an interval, we can fix randomness, fix the first bit of randomness of V so that they are equal to the bits of X. And just hardwire these bits into our machine. We obtain a new machine, which is denoted by V here. And that new machine will print our set with probability which is just equal to this conditional probability. And so we obtain a machine that prints our set with probability larger than 1/2. Is this clear? Please ask the questions if it's not clear. Okay.
So you want to then say that you want to take prefixes that appear with probability at least 1/2, and then they has to form a infinite branch or something like that.
How to show that A is enumerable given that machine? That's your question. No, we just observe that a number n belongs to A if and only if the probability that this new machine outputs n as part of this list is larger than 1/2. So we use this easy fact. And why is this? If, first of all, the implication from right to left, from left to right, if n from left to right, if n is in A, then with probability larger than 1/2, P outputs the whole list of A, and thus it outputs n. from right to left, from right to left, we can prove that if n is outside A, then the probability that V outputs n is less than 1/2. And why is this? If n is outside A, then again this probability more than 1/2 pre V prints A and not more than A. That means that it doesn't print n because n is outside A. And that means that the probability of not printing n is at most 1/2. The probability of printing n is at less than 1/2. So is it clear? I mean, this implication.
Yes.
And then we can just state that the probability that V outputs n as a function of n is semi-computable from below. That means that we can find estimates for that number from below with any precision we want. So just to enumerate, just running V on all possible randomness, on all possible random numbers. And if this probability is larger than 1/2, at some point we will find enough randomness.
So not with any precision we want. We don't control the precision, just
Right.
it will converge, but without any guarantee. No.
Right. It converges to 1/2, but we do not have a guarantee that we know that this estimate is very close to 1/2. But if it's true, at some moment we can understand that it is the case. And so we obtain that n is enumerable, A is enumerable, because we for all n is A, we can find some evidence of this fact by lower bound the probability that V outputs n. Sasha, what do you say? Do you buy this?
No, this I understand. I understood, yeah.
Okay.
This
So
is standard.
this was the easy part of the talk. Now, at some point, somebody maybe Solovay asked for a quantitative versions of both implications. So one implication has a very easy quantitative version. So I will write it on the next slide. So the first implication. This is the easy part. Assume that the complexity of enumeration of a set A is, say, at least 2 to the minus k. Oh, sorry. Assume that it is k, say. Then the a priori complexity of enumerating this set is at least 2 to the minus k up to some small factors. And these small factors is k squared times constant. More or less, this implication follows from the proof that if A is enumerable, then a priori, its a priori complexity is positive, as Sasha Kazachinsky provided. So let's see. This means that a universal algorithm D on some P prints A, where P has k bits. Then we can write this P in prefix code call it, say, head P, which is as follows. Say K zeros, then 1, then P. And consider then a machine which, after reading this prefix code of P, ignores the rest of input and just invokes D of P, printing A. Then for that specific machine, call it, say, V. The probability that V prints A will be equal to
But
2
to
to
do
the...
some strange thing, you double the length of P. It's
Okay, okay.
not a good idea, but okay.
No, it's a... Wait a bit. So we will obtain that the probability is just 2 to the minus the length of head P, which is 2 to the minus 2k minus 1. So this is worse than we wanted. Instead of 2 to the minus k, we obtain 2 to the minus 2k minus 1. And when we go to the universal machine, we will again lose multiplicative constant. But this idea may be improved by considering a better prefix-free code, a shorter prefix-free code. Call it, say, tilde P. So tilde P is obtained as follows. We apply this prefix code tilde not to P itself, but to K, to the length of P. And then we append P as it is to this prefix code. This will be also a prefix code because given that string, we can find K, read K bits, so we know when it ends. And now the length of this prefix code is smaller. It's the length of P, which is K, plus the length of the prefix code of K itself, but it is already 2 log K plus 1. And so we obtain, instead of this prefix code, use in the definitional V this new prefix code, and then we will obtain, instead of this, that the probability of enumerating the set is 2 to the minus this new code, which is 2 to the minus k over k squared minus 1 here again. And in this way, we obtain what we wanted. So more or less, if the complexity is k, of enumeration is k, then a priori probability is at least 2 to the minus k, ignoring polynomial small factors. So this is the first thing I wanted to say. Sasha, is it clear?
Yes.
Now, we want to prove the converse. If enumerating a priori complexity of A is at least 2 to the minus k, then the enumerating complexity of A is at most k plus something small, plus order log k. And unfortunately, this is unknown. Some partial results about this implication were obtained by Misha Ageev, as I remember, but very partial, so I don't recall the exact definition, the exact statement of his results. So this is unknown.
Mhm.
Okay.
And what's the problem with the so in the standard proof, we just enumerate, we know that there are at most 2 to the k
Now
natural
let's say the
numbers with
standard
that
proof. In the
probability.
standard proof, we use this fact about measures. So if the measure of a set is positive, then inside some interval it is large. But this interval can't be obtained in an effective way. So we can't find it. It might happen that that interval is very large. So x is enormously large. So we obtain actually no bound at all from this proof, because it's very non-constructive. So that's a problem with this proof. So Solovay got interested in this implication, and he proved the following thing. So Solovay's theorem reads as follows. If a priori probability of a set is at least 2 to the minus k, then its complexity is at most 3 times k plus order log k. So instead of constant 1, which we want to prove, he proved this implication with constant 3. So how I will now outline very briefly the proof of Solovay. So Solovay used the following Martin game, some game called Martin game. Some theorem of Martin. This is the famous Martin who proved that every barrel game is deterministic. And moreover, this Martin game was defined in that paper.
In which paper?
In the paper where it is proved that every barrel game is deterministic. So one of the player has winning strategy.
Okay.
And then I realized actually that from the same game, one can deduce that this inequality holds with better constant for finite sets. So if f is finite, and its a priori complexity is at least 2 to the minus k, then its enumeration complexity is most 2k plus order log k. And again, it is unknown whether even sorry, for of f, I meant here of f. And again, it is unknown whether for finite sets f, one can replace this constant 2 by 1. So unknown. Whether one can replace 2 by 1. So neither for infinite sets nor for finite sets, we do not know whether the constant with k is 1 or not. So these were quite old results, both of Solovay's and mine. And now the new development due to Shekhovtsov-Zakharov. They have shown that the constant 2 holds also for infinite sets. So if S is infinite and has a priori complexity at least 2 to the minus k, then its enumeration complexity is at most 2k plus order of k. And that's what I want to prove today or maybe the next time. And this is the result of this summer, more or less. And what's more important, they actually proved that the constant is the same for infinite and finite sets. So more or less, their proof is like that. Either from Martin game or even from my observation, they can make this conclusion. Sorry, again, I used A instead of S. So if we want to state their results in the most general and clean form, then it looks like that. So their theorem in the cleanest form is like that. Assume that a priori probability of certain set is small, is large, while the complexity of enumeration of the same set is small. Then the same holds for some its finite subset. With some loss of a priori probability. More specifically, the a priori probability of S of this finite set F given K and L, the pair of K and L is larger than 2 to the minus K over some constant D, call it D. And the complexity, enumeration complexity of that set is also at most L. So this is a reduction from infinite sets to finite sets. If S is finite, then the conclusion is trivial. We can take S as F, and so we obtain this. By the way, I haven't defined yet the a priori complexity conditional one, and this is defined in a usual way. Let's do it when on the slide when we have defined a priori probability. To define a priori probability, we just assume machines with auxiliary input. So assume that this machine, this probabilistic machine, has some input x, say. And then we again consider the probability that it prints A given X as input, and this will be called the conditional probability. And the theorem holds also in this setting, so the conditional probability for some machine is larger than conditional probability for any other machine. where the constant doesn't depend, of course, on the condition. And we call the a priori conditional probability given some with respect to some universal machine, a priori conditional probability. And
I'm
everything,
sorry, what is U of x in the definition?
facts.
U of x, you define conditional.
U of x. X is an input of the machine. So U reads X and then prints something on its output tape. So then we write.
So usually condition is given as an input to a machine.
Yes. Before you had no input at all. It was just
I see. Yeah.
But now we allow an input, and input is understood as condition. Okay. And so in our in the theorem of Shekhavtsov-Zakharov, we lose something because obviously the conditional probability distribution is larger. The conditional a priori probability is larger than the unconditional one. Sasha, is it clear that it is larger?
Yes, I assume yes.
And so for finite set, we lose something.
But I don't understand. So all this we lose just log some, I mean, or some polynomials in K and L in this case, in probability or no?
Sorry?
I mean,
when we put such a condition, then the a priori probability may increase by a factor which is polynomial in K and L. That's what I'm saying. Right?
Yes, is it true or no? Because I guess
true.
probably
Of course
no,
it's
because
true.
you would have
Of course it's
that,
true.
I mean, in the big.
Let's write it.
Okay.
What you said. So a priori probability of any set S given K, where K is a number, is at least the a priori probability of S without any condition over K squared times some constant. That's true, right? Indeed. And if we have two conditions, K and L, then we have the following thing.
For some reason, so on Zoom, you are still on page 5.
Right. That's very good because I have written this in the wrong direction.
Yeah.
The right direction is the following one. So there are a priori conditional probabilities, at least unconditional one times over some constant. And at most unconditional one multiplied by a polynomial of K. And the same holds for these two conditions. And that's because we just can consider a machine that first guesses that condition and then invokes the conditional machine. And the probability of guessing the condition is proportional to K squared, because we again can use the simple prefix code. And so the conditional probability will be larger than the conditional one, over k squared.
Yes.
Okay, and so from this Zakharov and Shekhavtsov, we can actually prove that the constant is the same for finite and infinite sets. Let's see how when can we deduce it. So the corollary. Assume that for finite set we have that if a priori complexity of f is at least 2 to the minus k, then the Kolmogorov enumeration complexity is at most, say, some function f of k. And assume also that f is computable and non-decreasing. Then we claim that for finite set, for infinite sets with the a priori complexity at least 2 to the minus k, it holds that the enumeration complexity is at most f of k plus something small, plus 2 log k plus some constant, plus some c, for some specific constant c. So if f is a linear combination of linear combination of k log k and constant, then obviously when we add to the argument something small, the constant doesn't change. The only change will be in the constant with logarithm. So that means that
Sorry, in the last line, C of F or of S?
Of S, sorry, sure. Of S. So why is this? We can imply we can apply Zakharov and Shekhavtsov for L, which is equal to this f of k plus 2 log k plus some constant. Now, assume that assume this. So we are given this, and also we are given this, and want to prove that the conclusion. So assume the complexity of S is large. Then, if its enumeration complexity is smaller than L, we have our implication. So we need to prove that the other case is impossible. So assume, for the sake of contradiction, assume that the enumeration complexity of S is larger than this L. Then we apply Zakharov and Shekhavtsov and obtain a finite set F whose enumeration complexity is large, Well, let's see how large is it. It's at least its conditional complexity is at least 2 to the minus k over d, and hence unconditional complexity is a little bit smaller. So the unconditional complexity, so F is a subset of S of unconditional enumeration a priori probability, at least 2 to the minus k over because L is a function of K and C, instead of K and L in the condition, we can put K and C. And so we obtain here K squared, C squared, times some constant. All right? And this implies, because we know that for finite set, the enumeration complexity is bounded by some function f of the logarithm of a priori probability, we know that the enumeration complexity of f is at most f of what? Of this guy, of k plus 2 log k plus 2 log c plus some constant. Because here is also a hidden constant, say d, plus constant. And if this constant c, which was not chosen yet, is large enough, this will be less than our L, because L is f of k plus 2 log k plus c, and here we have k plus 2 log k plus 2 log c. And we will obtain a contradiction. Right? Or not, sorry.
So I don't understand. I stopped understanding. So we want to know how much the enumeration complexity can be bigger than the a priori I mean this log of one a priori probability, right? Because it can only be bigger. I mean, up to everything logarithmic, right? So I'm trying to understand simpler thing, right? So, and then on the previous slide, you're saying that, okay, if I have an if I have an example
do you mean this slide, right?
Yes. So if I have an example where the a priori probability, the enumeration complexity is big.
I think that I confused on this slide. Sorry. Of course, there is a mistake on this slide.
So I guess you want to say that you can take a finite set that still has large enumeration complexity.
I confused the sign here. We assume that the enumeration complexity is large, but the
log of one of the probability is small, which means that the probability is large also.
The probability is large, that is 1 over log 1 over probability is small. And on the other hand, the enumeration complexity is large. And the consequences is like the same for finite set. Oh, that was my mistake.
Because, I mean, the other thing was kind of obvious, no? I mean, if you want to show this implication where the computer enumeration complexity is small and it still has to be small, you just wait for a subset that has large a priori probability.
I guess right. So it's not
But
interesting.
this
And the
now is,
interesting
yeah,
thing
this now is not.
is when one complexity, I mean log of 1 over a priori probability is large, but the complexity is also large. And the theorem states that the same holds for some finite set.
But the
Sorry.
theorem is just reduces this constant 2 to your old result, or it also gives a new proof of the constant 2 for finite sets? Or I don't
No,
understand.
no. This is only the reduction from infinite set to finite set. It doesn't prove anything for finite sets.
Well, so the Shkhartsov-Zaharoff result is is just a reduction, not a
Right.
new proof for finite sets, which is simpler
Right.
or something.
It's just a
Okay.
reduction. So, and let's finish the corollary. So once again, we want to prove that for any infinite set S with large a priori probability, its complexity is small. And how this is proved? Assume that the complexity is larger than that L. Then we can apply. Then we can apply Zakharov and Shekhovtsov. And to apply it, because we know that the a priori probability is large and also the complexity is large. So by their theorem, there is a finite subset of S with large a priori probability, but with small and also with large complexity. Right? By their theorem. There is a finite set F such that its a priori complexity is large, but Kolmogorov complexity of enumeration is also large. And on the other hand, it's impossible because for finite set, we know that if the probability, a priori probability is large, then the complexity is small.
Yeah.
We
So I
obtain,
don't know. I mean, I don't understand what you're trying to explain. I mean, why it's not obvious from the theorem. You're saying like the theorem shows that if one thing is large and the other is small, there is the same thing for finite sets. So I mean, then
right.
if you have an example of an infinite set where the one thing is 2 times bigger than the other thing, you have the same example for finite sets. So
More
the
or
same
less, this is
constant holds for finite and infinite sets up
yeah,
to some logarithm of k, l, and so on.
right. And there is also a small technical problem because
Yeah, so
with that constant C. So I just trying to explain how to solve this technical problem. But on the whole, you are right. This is an easy corollary of Zakharov and Shekhovtsov, right?
but what's the problem is that, I mean, the logs or something or
No,
what?
the problem is that we have here K and L in the condition. Assuming that we have no K and L in the condition, your argument is perfect. Right?
So you were explaining that we can derive from that just a priori probability is bigger than 2 to the minus k divided by k squared, l squared, and everything like that, no?
Right. Okay, right. And the point is that L is a function of K and C, our constant. So we can divide not by K, and if we divide by K squared, L squared, we do not obtain an upper bound for L itself as we want, because L comes also in the right-hand side of the inequality. We would obtain that C E of F is at most F of K plus 2 log K plus 2 log L. And why is at most L? It's not clear.
Well, I don't really see the problem. What's the problem with L? That it can be much larger than K or something like that?
It can be unrelated to K at all. If
Well, I know that it cannot be. Okay, well, you have some theorem that it cannot be like 3 times larger than K,
Mhm.
right? And I don't know. And we are interested in the examples where it's like 2 times larger, or maybe like
Okay, if you
1.5
use
times.
that Solovay's theorem, then probably you can finish the argument without this. I agree. Anyway, you are right. So let's forget these technicalities.
So can you show just write that in Shekhovtsov-Zakharov, just the complexity of f is larger than 2 to the minus k divided by something which is true by just, I don't know, by logarithm of k squared or something like that. I don't know.
So what's your question? Say it again.
So can I just write, so there is a theorem of Shekhovtsov-Zakharov. So in the conclusion of that theorem, can I just write that a priori probability of f is at least 2 to the minus k divided by some constant k to the 10 or something like that?
No, because we have also L in the condition.
No.
No.
Ah, okay.
But if we apply it to L as which is just a computable function of k, then we can do it.
Ah, yeah, okay.
So more or less, we apply it to L, which is a computable function of k. And in this way, we obtain in the conclusion that the a priori unconditional a priori probability is at least 2 to the minus k over d k squared. More or less,
So
this
you mean
is the proof.
if we had an example where L is 10 times bigger than K, we can just apply an L, I mean, and probably it can be something, some specific number, which is,
Which is
you know, I
complicated.
don't know.
Which is
So we can just
complicated.
take L equals 10 to the K and apply the, yeah, and then it will be
Right.
no problem.
Uh-huh.
Okay.
So more or less, the essence is that reduction. From that reduction, we can prove that the constant is 2 even for infinite sets. And if we prove in the future that for finite sets, the constant is actually 1.5, then also for infinite sets, we will have 1.5 and so on. So how much time is left? Almost no time left. Okay, now I think I want still to present the proof of Zakharov and Shekhovtsov, but now it's clear that tonight I can't do it. So now I will explain one metaphor, which is very easy, and somehow it helps to prove these all things. So this is our metaphor. Ants, it's called ants and cats metaphor. Assume that we have these universal enumerating machines. So it outputs a list of certain numbers, natural numbers. We can imagine, this is the probabilistic machine. We can imagine that actually its randomness is written on its auxiliary tape. So this is its randomness. Denote this by omega, this infinite 0-1 sequence. And let's imagine it as an infinite small amp. And now, assume that we run this machine on all possible contents on this auxiliary random tape. Of course, at each specific moment, that machine reads only a finite part of this tape, and we will think and assume that at a specific moment it has read some finite part of its randomness and output its some finite part of its output, like that, at a certain time t. Then we will think that all the ants which are continuation of this finite part, call it, say, x, sit on a vertex of the infinite binary tree in the vertex x. So this is x, and here sit some ants. So if the length of x is, say, L, that this is a portion of 2 to the minus L of ants. So, and assume that we run U invoking more or more randomness and probing all the possible randomness for U. This means that we will see that certain ants walk through this tree. So at the beginning, all the ants sit in the root. Then we will see that certain ants go to the left, certain ants come to the right. The remaining ants still are in the root, and so on. At each time of the simulation of the work of U, when something non-trivial happens, that means on some randomness, U prints some new number, that means that certain portion of ants walk along this tree in the direction upward. And actually, this is not a tree, because we will, because we are not, we will not distinguish between different sets if they have different orders. For example, it might happen that some portion of ones outputs 1 and 2 in this order, and another portion of ones outputs 2 and then 1. That means that both these portions of ants sit in the same node. So this is actually not a tree. So I made a mistake. This is a graph of finite subsets of n with the directed graph with the relation that one subset is a subset of another set. So we have empty set here, we have singletons here, we have two element sets here, and so on. So this enumeration may be viewed as a walk of ants through these infinite directed graphs. And if we use this ants metaphor, we can say that if the probability that U prints A some S is, say, at least 2 to the minus k, that means that some portion of at least 2 to the minus k ounce eventually make an infinite, if S is infinite walk, maybe using different paths in the tree, for the same set S. That so each ant enumerates a certain set S, which is the set obtained when we write this ant, this infinite sequence of bits, on its input tape. And each of these ants, corresponding to the randomness for which U prints S, make some walk, and in the limit, they, so to say, enumerate the same set. Sasha, is it clear? I mean, this ants metaphor. Sasha?
Sasha seems out of connection.
Misha.
To me, it's very strange why you are saying about ants and what are cats. Actually, to me, your picture corresponds another view. You have a unit amount of some liquid in the root. And then this liquid flows through this graph of finite subsets in some ways. This is not classical liquid. It uses different branches with different conductance, and it seems that it is exactly what I was saying, because your ant is a branch of infinite binary tree, and actually
No, this is not a binary tree. That's important, because we identify all the paths here which corresponds to the same set, enumerated set.
I don't understand. You need to assign some probabilities to this picture or on the graph of finite sets. And to assign these probabilities, you need to consider omegas as branches of infinite tree. Because
No. This is, maybe I confused you. This is not the branches of the tree. This is the numbers enumerated by omegas. So if at certain moment a certain ant sits here, for example, in the node 1, 2, 3, that means that at that moment the corresponding randomness has produced 1, 2, and 3, maybe in this order or another order on its output, on the output tape. So this the vertex of this tree corresponds not to the random input, but to the output.
Yes, I understand. But ant, as you explained, is an infinite string.
Right. Here are ants. Let's write a binary tree.
Yeah. So ants are in the infinite binary tree, and they mapped to this more complicated graph. It is not a tree.
Right.
Well, I understand the picture, but I don't understand the metaphor.
Okay. If you prefer liquid, I would say that certain molecules of that liquid are called ants. Okay. That's the same.
Yeah.
So the liquid flows through that graph. The root.
Yeah.
And certain or all the molecules are called ants. That's
Yeah,
okay.
yeah. Okay.
And the point is that each molecule or each ant can go only upwards.
Yeah.
So if something is already enumerated, we can't eliminate it in the future. We can
Exactly.
only enumerate more. And that's important. So what are cats? Cats are finite. So let's fix also D. The optimal machine to define complexity of enumeration. Then its input P of length less than L are called cats. So we have 2 to the minus 2 to the L minus 1 cats. And those cats also walk upward along this graph of finite subsets. If D on input P prints a new number on its output, we can imagine that cat moves upward the tree, up. So we can consider the following thing. We enumerate U and also we enumerate D, and cats and that results in both cats and ants walk along this tree upwards. And somehow this metaphor helps to understand what happens.
Okay, but maybe it's worth to explain in details next time.
Yeah, sure, I agree. Okay, then stop for.
Okay, thank you.
Okay, continue next time.
Okay.
Bye-bye.
Bye.
Thank you. Bye.